All right. So one thing that I really was glad to have this project done, I'm always sending people back to it. RSA keys are essential. You use them all in a lot of encryption, like encrypted email, and they're hard to understand. They're hard to write down and hard to recover. And one bizarre thing is if you want to understand the RSA key format, you can do it with OpenSSL, but only with the old version. The OpenSSL is upgraded from version 1 to version 3, and as far as I could tell, they've taken these functionalities out of it, although I can't find any writing explaining it. Um, so I actually figured out how to downgrade OpenSSL, which is the kind of thing I would normally avoid doing. But anyway, we already talked about RSA. You've got a lot of parameters. You've got prime numbers, P and Q. You have their product. You have Euler's totient, which is calculated from P and Q. You have the encryption exponent E and the decryption exponent D. And you need those numbers. And this is what an RSA private key syntax is right from the RFC that defines it. The RSA private key. You've got a series of these things. This is N, E, D, P, Q, and these other numbers. These are various parameters, really far more than you need, but it's all the parameters that are stored in a private key. And the way it's stored, it looks like this: begin RSA private key. This is the PEM format, privacy enhanced email. This is the most common way you see RSA keys. You see this plain text file. You have begin and end marks, and in here you got a blob of base 64. And what is in that base 64 is all of this information sort of encoded with some preambles. And OpenSSL used to have the ability to parse that, ASN1 parse. As far as I can tell, it no longer does unless you get to the old version. But if you do that, you can open up one of these and it will show you the quantities in there. The N, the public key, and the public exponent, the decryption key, P and Q, and then some other numbers that I didn't find that interesting. So there's a useful thing to know. Now, the public key, the thing you give other people, is much shorter. Begin public key in a shorter block of text because all it has is N and E, nothing else. Because that's the point. This is all you need to send encrypted messages, but you need this stuff to read encrypted messages, so the private key is bigger. And so you can make keys at a modern length like 2048 here, and you'll see them, and then you can open them up. And here you'll see the 2048-bit modulus expressed as a whole bunch of hexadecimal bytes. The exponent, like I say, people almost always use this number, 65537. And then there's the public key, which is much shorter, of course. Now, the key files themselves are typically encrypted with another layer of encryption with a password. Like I was saying, just like I was saying in the previous one for password-based key derivation, you have a vault, and what's in the vault is encrypted with another password, so that if somebody finds the file on your machine or steals it, they won't be able to get in because they don't also have the password. So that's what happens here. It's encrypted with AES, with cipher block chaining, which is perhaps not the best system, but that's what they're using. A lot of these are using pretty old techniques. And that's the game. And then I made some challenges for people to do where you have the private key, you have to open it, and the public key, you have to calculate from the private key. And then a couple that gave my students good time, I redacted parts of it, covering it with X's, and you have to recover the missing pieces. And here, so you have to take it apart and figure out what these missing pieces represent and figure out what you know and deduce it. So, and by the way, the easiest way I figured to find out what's represented by these characters was just replace them all by capital A and then replace them all by capital Z and see what changes. That's a brute force technique. But really, you know, base 64 just encodes the data 6 bits at a time instead of 8 bits at a time. So you could count things out and figure out just what bits of which parameter are being zeroed out here. But I didn't bother because the first one I made pretty easy, because I think you have P and N are not harmed. So you can derive Q. You don't really need the redacted part. Here you actually need some of the redacted parts. So you actually have to do a brute force search through something like 1 million cases to find one that'll work. Anyway, that's one that turns out to be real important as you have to move encryption keys from one format to another.